Some of our gas discussions, let's talk about the kinetic molecular theory of gases. This is a simple model based on the actions of individual atoms used to explain the behavior of ideal gases. There are 5 postulates to this theory. 1. Volume of particles can be neglected, but the volume of the container cannot. The smaller the container, the higher the probability of gas molecules having collisions, increasing the pressure in the container. Particles are in constant random motion. They move in straight lines in all directions and at various speeds. So the smaller the mass, the faster it moves, the higher the probability of collisions, and increasing the pressure in the container. There are no inherent attractive or repulsion forces. When molecules collide, the collisions are elastic. The total kinetic energy remains constant. There may be a transfer of energy, but none lost. The average kinetic energy of a collection of particles is proportional to the temperature. The higher the temperature, the greater the kinetic energy, meaning the higher the temperature, the faster the molecules will move, the higher the probability of collisions, and increasing the pressure in the container. Gas pressure is due to collisions of gas particles with the surface of the container. If we add up the forces due to all the collisions of the gas particles with the surface of the container and divide the result by the area of the surface, we get the pressure. Kinetic theory is also important in explaining the speed of gas molecules, which leads us to the following topic: diffusion and effusion. The root mean square, RMS, of molecular speed, in meters per second, is the type of average molecular speed equal to the speed of the molecule having the average molecular kinetic energy. It is given the following formula. Your root mean square is equal to the square root of 3RT divided by molar mass, where the ideal gas constant in this case is 8.31 kilograms meter squared divided by second square mole Kelvin. You got to use the right R to get units to cancel. Molar mass in this case is kilograms per mole. Temperature is in Kelvin, and the root mean molecular speed is in meters per second. Note the equation indicates that the larger the mass, the slower the molecule. Obviously, if molar mass is a denominator, if this number gets larger, then your speed has to go down mathematically. Diffusion is a transfer of the gas through space or another gas over time from a region of high concentration, more crowded, to a region of low concentration, less crowded. Effusion is a transfer of a gas through a membrane or an orifice. The equation of your RMS velocity of gases shows the following relationship between the rate of diffusion and your molecular mass. Basically, they're inversely proportional. This gets us to Graham's law. The rate of diffusion is proportional to 1 over the square root of the molar mass. We expect larger molecules, meaning larger molar mass, to move slower and hence slower diffusion rate. Once again, since this is in the denominator, as this number increases, the rate's going to have to decrease. The rate of diffusion and effusion of molecules from a container depends on 3 factors. First, the cross-sectional area of the hole. The larger it is, the more likely molecules are to escape. Second, the number of molecules per unit volume, meaning the concentration of the gas. The more crowded the molecules, the more likely for the molecules to diffuse. Third, the average molecular speed affected by temperature and molar mass. The faster the molecules move, meaning the smaller the molar mass, and higher the temperature, the higher the probability that they will be able to diffuse. So in summation, the temperature, the concentration, molar mass, and size of the actual hole involved in the gas molecules escaping affects the rate of diffusion and effusion. Therefore, if you compare the diffusion and effusion of different gases that are the same concentration, that are in the same container, and have the same temperature and pressure, then there's only one factor that will dictate the rate of the effusion or diffusion, which will be the molar mass of the species. According to Graham's law, the rate of effusion or diffusion is inversely proportional to the square root of the molecular mass for gases in the same container at the same temperature and pressure. The following relationships allows for the comparison of gases. We can talk about the rate of effusion of one gas, A, and compare that to the rate of effusion of a second gas, B. Notice in the formula that the rate of diffusion of A is inversely proportional to the molar mass of A, as well as the rate of diffusion of the gas B is inversely proportional to the molar mass of gas B. So here's a question. How much faster does hydrogen gas effuse through an opening than methane? We expect hydrogen gas to effuse faster than methane gas because it is lighter. It is a lighter gas. So we put it in the numerator just for our comparisons in this equation. We know the rate of hydrogen is divided by the rate of the methane, and then we have the molar mass of methane in the numerator and the molar mass of the hydrogen in the denominator with the square root of all that. So we plug in our values. We know that the molar mass of methane is 16.0 grams per mole. Molar mass of hydrogen is 2.0 grams per mole. So your units cancel. This has no units. Take the square root of that. That'd be the square root of 8, which gets me 2.8. So how we look at this is as follows. This is basically telling us that hydrogen effuses 2.8 times faster than methane. Homework 49.